Everyone, thank you all so much for joining us for the final Watershed Wednesdays webinar of 2025. Also on such a beautiful evening. I know it takes a lot to be indoors tonight, so I really appreciate you all showing up to learn with me this evening. My name is Amanda Cabanillas. I'm the Education and Outreach Coordinator at Greene County Soil and Water Conservation District. As many of you know, this was our third year running this webinar series as part of Schoharie Watershed Month. And it was a true pleasure to bring these sessions to you. Some of you have been here for most or all of these, which is very cool. So special shout out to those folks. Some of this year's and previous year's webinars have been uploaded to our YouTube channel, and you're welcome to go back and view those anytime. In case you don't know, Schoharie Watershed Month is a month-long series of free community events that celebrate and raise awareness of the waterways that flow across the Schoharie Reservoir watershed, as well as the 315 square miles of land across Greene, Schoharie, and Delaware counties that feed them. In addition to this webinar series, this year we also offered a guided Indigenous history walk at with Wild Hudson Valley at Westkill Brewery, a kayaking event on the Schoharie Reservoir, and the third annual Mountaintop Bio Blitz celebration at the Mountaintop Arboretum. We also hosted a community science data collection project on the iNaturalist app, where we encouraged community members to record their wildlife observations throughout the month in an effort to record as many species of plants, animals, and fungi as possible. At the end of the month, I just checked, we ended with a total of 339 recorded observations of 200 different species. Very cool. All Schoharie Watershed Month programs are offered for free to the watershed community and have been made possible by the Schoharie Watershed Stream Management Program, which is a partnership between Greene County Soil and Water Conservation District and the New York City Department of Environmental Protection. This evening's session, a Streamside guide to Catskill Mountain geology, will be presented by Dany Davis. Dany Davis is a geologist working for the New York City Department of Environmental Protection as the Stream Studies Coordinator and a fluvial geomorphologist. Prior to starting with DEP in 1997, Dany worked as a consulting groundwater flow modeler for 8 years. Dany studied geology in the 1980s at SUNY New Paltz and the University of Alaska. I've also been very fortunate to spend many hours in various streams with Dany over the years, and I'm very excited to host him with you all this evening. This presentation will last. Yes, yeah, we were out there this morning. So we'll plan to be on here for about an hour presentation time, and then we'll take some questions at the end. Please feel free to use the chat or the Q&A box to submit those questions. If using the chat, just make sure that your chat function is set to go to everyone. So with that, I will turn it over to you, Dany.
Okay, thank you. Hi, everyone. And some of the information that Amanda said, since 1997, studied geology in the 1980s, gives you an indication of my age range. So I've been doing this for quite a while, but I still consider myself a student. And what I wanted to do with this opportunity that Amanda offered is sort of have like an introduction to Catskill Mountain geology that you can experience through streams. So the talk that we're going to do, I'm going to go over all the details in a moment. I've practiced it twice. And it's taken me about 50 to 55 minutes if I stay on script. So my goal is to stay on script, take us through the set of slides that I have, and then be available to you to answer questions. So if you have questions, please put them in the Q&A category, maybe rather than the chat, but if that works for you, please do that. And then we'll just try to take these questions as in the order that they come in. So first thing I have to do is share my screen. Is that correct? Let's see. I recommend that if you can, just minimize the little talking heads up in the right corner if you have that in your screen so that you can just see all of the images that I have for you. This is a very image-driven presentation. Okay, so this presentation is intended to be a virtual Streamside guidebook to exploring Catskill Mountain geology. I want to emphasize first, though, that I am not an expert on Catskill geology. There are geologists in the area that know far more than I do about the geology of this region. And I hope you were actually able to catch Dr. Chuck Verstraeten's talk last week for the deep dive into the Devonian period history of the Schoharie watershed. It was recorded, so please check it out if you didn't. And Dr. Andy Kozlowski's talk last year about the glacial history of the Schoharie watershed, which was not recorded. This talk is going to sort of deal with both of those topics, but how you experience them through streams. And what I bring to this presentation as a fluvial geomorphologist is a lot of experience in studying Catskill streams and their relationship to Catskill geology. I'm going to define fluvial geomorphology for you in a little bit, but I want to emphasize that this talk is for the broader Catskill High Peaks region and not to the specific reservoir watershed, say for Schoharie or Esopus or Rondout or the others. I also like to get my talk started with a question. And so for this talk, here's my question for you all. Why use streams as an entry point to learn about the geology of an area? And I know you cannot answer that question directly to me, but please feel free to put your responses in the chat and we'll check those out later. But since this is a webinar, I'm going to just jump right to my answer for you, and no answer is the absolute correct answer. And the answer that I came up with is that streams are just great geologic storytellers. And if you know how to listen to or read the stories that are there to learn, we can find out a lot about the geology of a stream's watershed. The results of stream erosion and sediment transport dynamics affords access to investigating the geology in a setting that, in our case, is mostly covered by vegetation. What you'll need are some skills and background information for reading stream geology stories, but mostly just plenty of time visiting streams and having a curious and inquisitive nature will be sufficient to get you started. And reading a stream's geologic story involves learning the language. So what I aim to do with this is get us an introductory start on that today. And before I leave this slide, I just want to point out these two photos because we're going to kind of touch on them as we go through the presentation. The photo on the left is Black Chasm Falls in Platte Clove in the Plattekill watershed. And that is a tributary to the Plattekill that is flowing over a Devonian fluvial sandstone cliff. And hopefully, by the time we get to the end of this talk, for those that don't know what that means, it will actually make some sense for you. And then the photo on the right is eroding terraces on the Stony Clove Creek that's in the Esopus Creek watershed. And what we have here is an exposure of Pleistocene glacial till capped by Holocene alluvium. And I hope that by the time we get to the end of this talk, that will make some sense to you. Okay, so here's what we're going to do. First, we're going to start with a brief spatial introduction to where the Catskill Mountains are. Then we're going to take a few slides to discuss how we can read the landscape to learn about the bedrock of a mountainous area and the forces that shape it. We'll follow that by talking about three distinct geologic periods that we can investigate in the Catskills: the Devonian bedrock history, which is what Dr. Verstraeten talked to us about last week, the many tens of millions of years it takes to shape the Catskill Mountains, and then the recent glacial history. Then we're going to spend the remainder of our time relating the geologic history to what we can actually experience through streams. Okay, so chapter 1 of our guidebook is where and what are the Catskill Mountains? And for those that don't know the Catskills, let's get some spatial context. This is a webinar, so I have to make that assumption. So where are the Catskill Mountains? There they are, up on the northeastern corner of the North American continent on planet Earth. Kind of puts us in the neighborhood. So if we zoom into the mid-Atlantic and northeastern North American coast and the interior, we can see that the Catskills are located in the northern part of southeastern New York State. We're going to zoom in even further, and we're going to enhance the terrain in GIS so we can see the boundaries of the Catskill Mountains, and I'll highlight those for you in just a moment. For those that don't know, GIS means Geographic Information System. It's a computer software system that analyzes and visualizes geographic spatial data, such as topography in this case. As you'll see, I've used it extensively to create topographic visualizations for this presentation. And before I leave this slide, I just want to highlight the boundaries. So they're bordered on the east by the Hudson Valley, and I'd see if I can get a mouse over here. Hopefully you can see that. So they're bounded on the east by the Hudson Valley, on the west by the Susquehanna River Basin terrain, and on the south by the Rondout and Neversink valleys, on the north by the Schoharie and Mohawk River Basin terrain. However, this sort of northern and western boundary is a little fuzzy as to where the Catskill Mountains end and the hills begin. And that's part of the story. So I'm going to take that same data from that previous slide, and I'm going to use it as an oblique aerial view, like I'm flying over the terrain. And we can see the Catskill Mountains really pop out of the landscape. This image is a 3D projection of what we call a bare earth digital terrain model derived from airborne LiDAR data. And if you caught Chuck's talk last week, he talked very excitedly about the value of LiDAR in the geologic research that we do. And LiDAR, LIDAR, stands for Light Detection and Ranging. LiDAR is a remote sensing technology that uses laser light to measure distances and create detailed 3D representations of a surface. It works by targeting an object or surface with a laser and measuring the time it takes for the reflected light to return to the receiver. For terrain surfaces, the LiDAR sensor is usually on an airplane or drone flying at a fixed altitude. And depending on the area covered, many hundreds of thousands to millions of LiDAR points are collected. To produce a bare earth digital terrain model, all the vegetation and buildings have been removed from the LiDAR data to just look at the Earth's surface. So that image that you see is just looking at the surface of the Earth with everything else removed. The resulting data we geoprocess into what we call a raster file. Basically, what that is I have this set up so that it's every square meter, and I have an elevation value for every square meter. So I get really high resolution maps like the ones that we're going to see today. The different colors in this map represent different elevations, and the result is what we call a shaded relief map that helps us highlight the terrain. Okay, and just a couple of more ways to sort of orient ourselves. We have the eastern escarpment of the Catskills here, which is bordered by the Helderberg Escarpment. We have the Hudson River Valley. I live on the northern Shawangum Range, right about there. And we have the southern escarpment in this area here. This is the Slide Mountain, Panther Mountain area. The central escarpment is the Devil's Path area and beyond. And then we have this fuzzy western boundary out to the west there. All right, so that was sort of our basic introduction to the Catskill Mountains location. So chapter 2 is going to be reading the landscape. And this chapter is intended to give us a brief introduction to geomorphology and using maps to help read the landscape and provide some context for what you might see in a stream channel. I could spend an entire day on this topic, but promise not to do so. So we're going to move right to this slide that offers us a definition of geomorphology. It's the study of the Earth's surface landforms and the past and present processes that shape the landscape. This is a photo that I took from the summit of Cornell Mountain, looking across the Woodland Creek headwater valley over to Panther Mountain. And I guess I should just say that this is one of the areas I have probably explored the most in the Catskills and one of the places that I have learned the most about streams and geology. And specifically, I study the discipline of fluvial geomorphology. And so what do we mean by that? Fluvial means pertaining to rivers and streams. Geo means pertaining to earth. Morphology is the study of form and formative process, like in our past definition. So geology is the study of landforms and their formative processes. And fluvial geomorphology is the study of river form and formative process. And I borrowed this slide from one of my colleagues, Telemaque Olson. I want to highlight that landscape holds the memory of the past. So the landscape that we see today, anywhere really, integrates the terrain's geologic and climatic history, and in our case, into the unique Catskill Mountains. So in this image, I've used a color shading that helps emphasize the location of the Catskill Mountain high peaks. These are the summits with what looks like a coating of snow on it, that white. I've labeled Panther Mountain with its unique circular drainage pattern or annular drainage pattern, since it really stands out and it helps us reference the rest of the landscape. We're going to kind of come back to that throughout this presentation. When we look at this landscape, we can see mountains and valleys, or I hope You can see mountains and valleys in this image. We can also see some patterns in the mountains and valleys, such as similar trends in stream, valley, and ridgeline orientation. So here we are looking at the central escarpment, and we can see that these all line up. There's patterns in this landscape. The streams have a similarity in their orientation. A lot of these are draining to the southwest. These are draining to the southwest. This is draining to the north. We get this unique pattern here. So we can use drainage patterns to give us some clues to the nature of the bedrock and the geologic history of this terrain. Before I step into a stream, though, I like to do my homework before I investigate the geology of an area. And maps are among our most useful and available tools for interpreting the geology of an area, especially a mountainous area where topographic relief and stream drainage patterns can tell as much about the composition and the history of the terrain. So this is a topographic map, USGS quadrangle map of a portion of the central Catskill Mountains featuring Panther Mountain in the Esopus watershed and Westkill Valley in the Schoharie watershed. And if you can see my cursor on the screen, this is the Westkill Mountain. We live in a time when maps like this can be downloaded from the internet and accessible on our phones, tablets, computers, or can be printed if we have that option. There are also several maps in our apps designed for hiking that have great topographic info that's actually more user-friendly than these USGS maps. But I like to start with topographic maps first. Then, if possible, I like to look at a bedrock geology map. I like to look at geologic maps. So this is a bedrock geology map of that same area. And so let's first start with what is bedrock. Bedrock's the solid, consolidated layer of rock forming the foundation upon which the Earth's surface is built. Bedrock can be exposed at the surface or it can be buried under layers of weathered rock. We call that regolith, sediment, and soil above it. In the Catskill Mountains, the bedrock is at least a mile-thick sequence of sedimentary rock composed of Devonian-aged mudrocks, sandstones, and at the higher elevations, conglomerates. And we're going to have more on this in chapter 3. But I wrote this that it was about a mile thick, but last week Chuck told us about 1.6 miles thick of this sedimentary rock. This is a surficial geology map of that same area. Surficial geology refers to all the earth material that covers bedrock. This is the stuff that I actually study. This includes sediment deposited by streams, lakes, glaciers, wind, anything that can move sediment from one place to the next place. It includes the soil and weathered bedrock on forested mountain slopes, anything on top of the bedrock. In the Catskill Mountains, the superficial geology is a combination of glacial deposits and fluvial, which means stream, deposits. It can vary in thickness to just a thin veneer over bedrock to hundreds of feet thick layers of glacial sediment in valley bottoms. And we're going to cover more on that in chapter 5. But I realized I forgot something, so I have to go back a slide to the bedrock. What I wanted to point out is all these colors represent the different bedrock formations in the Catskills. And out here, this is the Ashokan Reservoir in the lower right-hand corner. I don't know if you can see my cursor, but these colors represent different bedrock formations. And I've got the list of those formations up here or symbols of those formations up on the upper right of the map. And as you go up in the terrain, you are actually advancing through time. And so we're going up, and all of these rocks tend to be, as I mentioned, mud rocks and sandstones in the lower elevations. And then as you go up a little bit higher and you get up into like Panther Mountain, Slide Mountain, you start to get a lot more conglomerates. In the surficial geology map, what we can see is the red on this map is rock, but we know that the Catskills are not this much exposed rock. So this is an example where there's just a thin cover over the rock. But once you get into the valleys, you start to get a lot of the sediment. The purples represent something called glacial till, which we'll be talking about. The yellows and oranges are stream deposits, and the greens represent ice margin deposits. And we'll discuss some of that as we go forward. But one of the things I wanted to highlight is look at the Esopus Valley. Here's Panther Mountain. Look how much exposed bedrock there is here, or bedrock barely covered by sediment, compared to the Schoharie Basin and how narrow the valleys here are, and then in the Schoharie Basin, how broad the valleys are. That represents the different glacial and bedrock histories. Okay, so I've returned to this 3D map. The thing that I want you to notice how most here is how crenulated or wrinkled the surface is. Each crenulation, small to large, is a valley or drainage formed by water flowing across the landscape in channels. Each channel exposes and samples the surface geology it flows across. We know that streams carry sediment, so this is where it gets its sediment from. We can see from this map that streams actually occupy much of the Catskill landscape. In fact, we could say the Catskill Mountains are a landscape story scribed by streams. It's essentially a fluvially defined landscape, and we'll discuss that in more detail later on. But the main thing to know here is that the bedrock and the glacial history influence the landscape fluvial drainage pattern. So let's talk about landscape drainage patterns. So Watershed's drainage pattern can tell us something about the bedrock. We've not yet discussed the bedrock geology of the Catskills beyond the fact that it's largely those layers of sandstones, mud rocks, and conglomerates, as shown in the bedrock geology map and as discussed in wonderful detail by Chuck last week. Here are 4 examples of drainage patterns that can clue us in on the bedrock composition of an area. So I'm going to review each of these really quickly. On the upper left, we have a dendritic pattern, which develops on relatively uniform bedrock, and dendritic refers to the tree-like aspect of this drainage. B would be a radial pattern, and that's streams coming off of a cone tape or dome type landform in the landscape. Clearly, that is not our situation. C, rectangular pattern, is something that is a drainage pattern that develops on highly jointed or fractured bedrock, so the streams tend to follow the network of those fractures. And then D is a trellis pattern, which develops in areas of alternating weak and erosion resistant rocks. So you can see, like in this example, the ridges are resistant rock and the valleys are less resistant rock. In the Catskills, we have a combination of dendritic, trellis, and to some extent rectangular patterns. So let's look at that in a little bit of detail. Westkill Valley is both a typical and an unusual watershed. We'll cover that. The drainage pattern is predominantly a combination of trellis and dendritic, which is typical for the sedimentary bedrock that comprises the Catskills. So because we have those mud rocks, they're very prone to erosion. If you attended Chuck's talk last week, he talked a bit about that. And then the sandstones are very resistant to erosion. So we get that trellis pattern superimposed on that dendritic pattern, the tree-like pattern. So when you look at a map of the Catskills, you're sort of seeing a blend of those 2 drainage patterns. Another thing that we can do with maps is look at the longitudinal profile. That's the slope from upstream to downstream. So this is Westkill Stream. It originates up on Hunter Mountain and flows all the way down to Schoharie in Lexington area. The longitudinal profile is a wonderful way for you to sort of look at the different kinds of geology you might see as you go from upstream to downstream. And that's what I'm going to focus on. But we could also, if we had the time, look at the fact that this is a U-shaped valley instead of more of a V-shaped valley here. So a lot of these valleys in the Esopus system where we can see the influence of streams, but here we actually begin to see the influence of glaciers. And hopefully we'll have some time to talk about that. Okay, so here's what a longitudinal profile looks like. Here's the upstream end, and it originates on Hunter Mountain and descends the slopes in a series of cascades, waterfalls, and boulder step pool channels. This is also where there can be a lot of active erosion into slopes, causing small to large landslides that bring in new sediment to the stream. Once the stream leaves the mountain and enters into the broader Westkill Valley, it has less energy, but still has sufficient slope to transfer a lot of the sediment it is transporting and eroding. It can have a lot of boulders, as it does in this case, in this image. This tends to be a very dynamic section of stream with lots of erosion into glacial legacy sediment stored in the valley bottom and margins. So this is where I spend a lot of my time. Further down valley, the stream slope lowers further and the transport capacity drops. And we tend to see a lot more depositional features. And in the Westkill, there's actually an extensive braided channel that runs along New York Route 42 for those that are familiar with the area. If I'm going to explore the geology of the creek, I'm going to have very different experiences and exposures depending on which section I visit. So if I want like a sample from the entire watershed, I'm going to go all the way down towards Schoharie Creek, and that's the area that's going to represent the entire watershed. So just to summarize that, when we go from headwater reaches to the downstream reaches, we get to have different geologic experiences. In the headwaters, there's a lot more bedrock and boulders for us to do more detailed examinations of the rock within the watershed. And as we go down valley, we get the benefit of more and more terrain being sampled, but we actually get smaller and smaller rocks. So I like to sort of sample throughout a watershed. All right, so that's sort of just the reading the landscape. So we're going to jump right into chapter 3, the Devonian Catskill ancient rivers and forests. And this is what Chuck took an hour to talk about last week. I am going to have about 10, 15 minutes. But what I want to note here is that the image I used came from a public domain source, and it's some artist's rendering of what a Devonian forested river landscape might have looked like, not unlike forested river landscapes we see today, draining high mountains down to lower elevations, and in this case, ultimately to a sea. But what I appreciate about this image is actually how blurry it is. It underwrites how I can really only vaguely imagine what it would be like if I was dropped into the Catskill region in the late Devonian period. So I actually decided to stick with this one because it's closer to the truth for me. But before we get going any further, what do I mean by the Devonian period? The geologic timescale uses the Earth's rock record to organize time into named periods. Earth scientists use this chronological dating system to study and reference the history of the planet. If we use the analogy of a 24-hour clock, like I have here on the right, to represent the 4.543 billion years of history, we can get a sense of the magnitude of deep time. So I'm going to switches over to this. The last 17 seconds, there's actually only 2 periods of time represented in Catskill geologic material, whether it's bedrock or superficial geology. The uppermost is the superficial geology, and the last 17 seconds in our 24-hour clock represents the Quaternary. That's a period that includes the most recent ice ages that filled the Catskills with ice repeatedly over the span of the last 2.6 million years. So 2.6 million years equates to about 17 seconds. The Devonian period, which occurred about 359 to 419 million years ago, an unimaginably large amount of time, would have been between close to 9:50 p.m. on our clock to, about halfway past 10:07. And that 60 or so years actually includes just the 5+ million years when the sediments that formed the Catskill bedrock were deposited. So in our 24-hour clock, there's really less than a minute of time represented in the Catskills. Catskill Mountain bedrock geology is a sedimentary record of Devonian river systems, which Chuck talked about last week. So the rock that we see in outcrops and in streams in the Catskills is essentially the fossil remains of these ancient rivers and floodplains. So each layer in this Catskill sandstone, I've got this photo of, is a depositional event. Sand was transported in a river, then deposited and stored for hundreds of millions of years. We can also see in this image, and again, I don't know if you can see my mouse, that one set of layers crosscuts another set of layers. That records an erosive event and a subtle change in the river bed form. So these are actually little migrating dunes. So not only do we see the products of ancient river deposition, the layers, but we actually also can see the process recorded in the deposition that has been preserved in this rock record. So in this outcrop, we're looking back in time when a sand-bedded, low gradient, low slope, meandering river was moving sand and water from ancient mountains to an inland sea. And the bedrock is this repeating sequence of 3 categories of sedimentary rock. Sandstones, and you'll see on the photos, I label those SST. Conglomerates, I label those as CGL. Those are sand and gravel stones, if you want. Mud rocks, I've labeled as MRK. Those comprise a wide variety of fine-grained silt and clay rocks, like shale, siltstone, and mudstone. So there are fine sediment rocks. The sandstones and the conglomerates are erosion-resistant rocks, while the mud rocks tend to be very prone to erosion. I'm going to repeat that repeatedly throughout this talk. Hence, they actually influence that trellis drainage pattern. Also, they influence the stair-step profile of the Catskill Mountains, and we're going to see that in a little bit. All right, so I hope you're able to catch Chuck's talk, but if you didn't, I've lifted some graphics from one of his publications. The photo here is actually my photo. It's a typical example of a sandstone layer above a mudrock layer. And what we see in the Catskills is mudrock, sandstone, mudrock, sandstone, mudrock, sandstone, maybe some conglomerate, mudrock, sandstone. We get this repeating sequence representing the millions of years of these rivers occupying a portion of the landscape. So the story these rocks tell is of these meandering rivers flowing across a broad forested delta. In this block diagram that Chuck included in his paper, and I believe in his talk, we see the Acadian Mountains to the east. This might be around the Massachusetts, Connecticut border area. And the Catskill Rock is just this narrow band where you can see these green trees. And then out in this area, in the lower area, that is a sea. So the Catskill bedrock represents this relatively narrow band, this alluvial plain of the river sediment and floodplain sediment. How big were these rivers? We weren't there to witness it. So we actually have to use science to figure that out. And John Bridge, a geomorphologist and sedimentologist at SUNY Binghamton, found that the rivers ranged in width from about 100 to 1,000 feet wide and possibly had a mean depth of about 6 to 23 feet deep, very specific. That block diagram sort of highlights their setting, as I said, and the stratigraphic column on the right emphasizes where I put this red boundary around this. These are the rocks we see in the high peaks, the Oneonta Formation, the Walton Formation, and the Slide Mountain Formation. As we go to the margins of the Catskills, we might encounter the Manarkill, the Plattekill, and the Ashokan. The names don't mean much. The main thing to know is that as we go up in this sequence, the rocks get younger and the rocks get coarser. We get more and more conglomerate at elevation. So the sandstones and conglomerates are the river channel sediment, and the mud rocks largely represent riparian floodplains, though they could also be deposits in ponds and lakes formed in those Devonian Valley bottoms. If you look at some of the sandstones, you're going to find fossil remains of riparian forest fragments. I've got some photos of that for you in a little bit. And in the mud rocks, you're actually going to see root casts. So I've got an example here on the upper right, those little stippled patterns, those are actually the casts of roots from the riparian or streamside forests of the Devonian period. Also, in some locations, you might actually find that the red mudstones, here's sandstone on top, mudstone on the bottom, actually have green inclusions. What are those? What's the story? Well, most of the mud rocks that we see in the Catskills tend to be red because of oxidized iron. They are exposed to oxidized iron, but the roots in the subsurface, once those roots start to decay, they might fill in with sediment, but because they're not exposed, that rock actually has more of a reduced color, so that green color. So we can actually literally look at fossilized subsurface groundwater conditions when we're looking at these red and green shales. So I'm going to zoom us back out to the landscape scale. And I would just want to highlight how the sedimentary layers form the distinctive mountain slope profiles. So you can see this is a view of the eastern escarpment of the Catskills. The canyon that you see, or the gully, the large valley that you see in the center of this, that's the Catskill Clove. Okay, so we have Catskill High Peak here. This drainage that you can see, this broad valley, that is the upper Schoharie Valley. And what you can see is this stair-step pattern. So the steps or the rises are the sandstones, and the treads, the lower slope areas, that tends to be where the mudstones are. So you can see that repeating sequence just in this profile. The other thing I want to highlight is that the bedrock is also fractured with joints, and we'll talk about that in a little bit. But those two, the combination of the horizontal layers and the vertical layers, actually sets the pattern for how these mountains are made. So chapter 4 in our little guide is how the mountains are made. So there are many kinds of mountains and mountain ranges on planet Earth, and many ways to make a mountain and a mountain range. In all cases, there are forces that raise the Earth's crust up and forces that work to lower that elevated terrain back down to some base level. The unique characteristics of the world's mountains are essentially expressions of the balance or imbalance of those competing forces, the nature of the mountain bedrock, some bedrock is easier to expose than others, or erode than others, and the time involved. So I picked these two photos. There are peaks that I love to hike and climb and have similar elevations. Wittenberg Mountain on the left is in the Catskills and is about an elevation of 3,780 feet. And Bear Mountain in the Kenai Mountains of Alaska on the right has an elevation that's only 330 feet higher, yet clearly they're quite different mountains. The Kenai Mountains are babies and are still rising from crustal plate convergence where plate tectonics is involved, and glaciers and streams are working hard to remove the uplifted rock, but cannot keep up with the rate of uplift. The result is the more jagged and rock-exposed mountains you can see in this photo. The Catskills, however, are actually quite old mountains, many tens of millions of years old to maybe older if you consider their complicated history. The process that uplifted this terrain ended long ago, and the various climates over this long period of time have carved these peaks of undeformed sedimentary rock. So the Catskill Mountains are a remnant landscape of a broad uplifted plateau carved into mountains and valleys by tens of millions of years of stream or fluvial erosion and that last 2.6 million years of recurring glacial erosion. So I wanted to zoom back out on this slide so that you actually get a sense of how the Catskills fit into the broad continental scale. So the Catskills are at the northeastern end of the physiographic province called the Allegheny Plateau, which occurs to the west of the folded and faulted Appalachian Mountains and extends south to Kentucky. So you can trace this plateau all the way down to Kentucky where it becomes the Cumberland Plateau. And the Catskills are that northern and higher elevation extent of this continental scale feature. So we're going to zoom back into the Catskills to highlight once again the stream-striped landscape. What are the geomorphic processes primarily responsible for producing this unique mountain landscape? First, we need to recognize that unlike the earlier example of the Kenai Mountains, where the process of mountain formation is this imbalance of crustal uplift exceeding the erosional processes that can wear the mountains down, Catskill Mountains are largely defined by the excavation and evolution of the valleys. So in a sense, when we're talking about Catskill Mountain making, we're actually talking about Catskill Valley evolution. So I've got a few slides on that. Valley evolution in the Catskills happens through streams eroding, entraining, and episodically moving sediment downstream and ultimately out of the valley. Floods from small to unimaginably large, cumulatively occurring across the span of millions of years can export a lot of mountain material. So the primary driver sculpting the Catskill Mountains out of a plateau is climate. And in particular, it's the hydrologic flood regime of the climate. And then later in the Pleistocene, the glacial regime. The climate of the last many tens of millions of years has changed repeatedly with warmer, wetter periods and colder, drier periods. But throughout this time, when not covered by the glacial ice during the Pleistocene, the Catskill terrain has been subject to this range of constructive smaller floods to destructive larger floods. And I think of the mountain and valley altering 2024 flooding from Hurricane Helene in the Appalachian Mountains of North Carolina and East Tennessee. That's what comes to mind for me when I try to think about the scale of some of the floods that happened over tens of millions of years. So I just have these two images. The image on the right is Stony Clove Creek during a 2 to 3 year flood. So it's going to occur every 2 to 3 years on average. And it's moving sediment. It's moving suspended sediment. And probably if you were with me on the bridge when I took this photo, you might be hearing some boulders moving. The image on the left is actually a simulated 500-year flood in a hydraulic model for the Upper Sopus Creek Valley. So this is not a real flood, this is a modeled flood, but it gives us an idea that when we get a 500-year scale flood, it is filling the valley floor. It is moving sediment out of the system. So imagine a 1,000-year flood. Imagine something even greater, and then apply that over tens of millions of years, and you can get some mountains. So valley evolution is also happening across that same span of time through the persistent and episodic application of stream power, that flooding stream power, which is the stream flow times the slope or the energy available, and that erodes into the valley margins. So flood-induced stream bank erosion leads to the lateral migration of channels in the valley floor, moving back and forth. And the entrainment or removal of that sediment that's stored in the valley bottoms and margins is exported out of the valley ultimately. The stream often erodes into its own former deposits of stream-transported sediment stored in the floodplain or the valley bottom, and we call stream-sourced sediment alluvium. This recycling of alluvium is part of the millennial to million-year scale transport of sediment. The stream also erodes into glacial legacy sediment from the ice ages. I have an image of that on the right. This is one way that new sediment can get into the stream system, and how the mountain valleys and slopes are still influenced by the glaciers of thousands of years ago. Valley evolution happens across that same span of time through the persistent and episodic application of stream power again. But this time, instead of forcing the stream to move laterally, it's causing an incised landscape. So some floods are capable of causing stream channels to cut down into the landscape. And this is largely in response to some lowering of the channel base elevation downstream. And at the abrupt change in bed elevation, where you see that abrupt change in lowering, we call those nick points. This lowering can occur at the continental scale with changes in sea level and incision occurring over the span of thousands to millions of years. Waterfall formation in bedrock takes place over this span of time through this incision process. So each waterfall is a nick point, and it's not a static point, but in our lifespan, it tends to be static, but over the span of thousands to millions of years, it's not. The lowering can actually also occur at the valley or stream reach scale in response to stream channels being straightened downstream and steepened, or base levels lowering in a main stem stream that forces lowering in a contributing tributary. I have an example of that on the right. That's Warner Creek. And you can see the nick point here where we go from the very bouldery stream bed where the stream cut down into some glacial till. And this happened after Tropical Storm Irene in 2011. So overnight, this waterfall formed. All right, so valley evolution also happens through the persistent and episodic occurrences of mass wasting or landslides in an incised landscape. So the basic process here is as the valley bottom lowers, the valley sides can locally steepen, becoming unstable and prone to landslides, often triggered by storms and floods. Bedrock slopes are more resistant than the glacial sediment slopes, so this is not a process that occurs uniformly across the landscape. We can see this process of mountainside making going on today, as evidenced in these photos. The photo on the left is one of the bigger active slides in the Esopus Basin, and you can see me digging into it for some scale. It's well over 30 meters high and easily 30 meters across at its widest part. And I was able to track sediment coming from this slide at least a kilometer downstream. It's a great example of active Catskill mountain making going on by transferring sediment from the mountain sides to the valley floors for ultimate export out of the watershed. And I have just a couple of other examples of landslides here in the images. All right, so this process, there's a lot of parts to this process, also continues through the continuous process of bedrock, chemical, and mechanical weathering. And this process takes advantage of those vertical fractures I referred to earlier, intersecting with the sedimentary depositional layers. An example is an application of the freeze-thaw process in fractured bedrock that degrades the rock's integrity and makes it prone to rockfall and talus formation. The photo on the left is of a cliff outcrop on Slide Mountain, illustrating that fracture network that makes Catskill rock so easily to be quarried either by natural processes or even by humans. The photo on the right is an example of the product of that process. It's a bare talus slope composed of blocks of rock eroding out of a twin mountain cliff band in the central escarpment. So I want to close this chapter by talking about the Panther Mountain mystery. I have featured photos and maps depicting Panther Mountain in this presentation. I'm going to just circle this little drainage here. So let's briefly discuss the unique feature in the Catskills and how it supports the premise that the nature of the bedrock defines the mountain and valley formation. The unique circular drainage that defines Panther Mountain's base is really unusual, not just in the Catskills. And in the 1990s, Dr. Ingvar Isaacson of the New York State Geological Survey hypothesized that this could be the result of preferential stream erosion of bedrock occurring along the margins of a deeply buried small asteroid impact crater that would have formed in the Devonian before the Devonian Catskill River Delta sediment was deposited. So the rocks we see in the Catskills would be deposited on top of this crater. We don't have time for me to discuss all the circumstantial evidence that Dr. Isaacson and others assembled to support their hypothesis, but I can say it included observed increased bedrock fracture density in the feature defining channels of the upper Esopus Creek. That's, I don't know if you can see my mouse, going around clockwise, and Woodland Creek, creating that circle. And that would be the rim of this crater. It's a fascinating origin story for a unique feature. I say it's still a hypothesis, though. It's not been adequately proven or disproven, but the circumstantial evidence suggests it's our best origin story that we have for now. And it's a fun one to tell. All right, so chapter 5, the Pleistocene, glaciers, ice sheets, and lakes. We've covered the role of streams in defining the Catskill Mountain landscape. However, the geological process that has most recently helped form the Catskill Mountain landscape, and what brought me into geology, is the repeated glaciations of the past 2.6 million years during the Pleistocene epoch of recurring continental scale ice sheets and possibly localized mountain glaciers occupying the Catskills. But when we think about glaciers in the Catskills, we're thinking about these large continental scale ice sheets, not specifically smaller glaciers. We don't actually have images, of course, of what the Catskills look like during the Ice Age. So here's a photo I took of Exit Glacier, that would be a mountain glacier, and the Harding Ice Field, which would be somewhat similar to an ice sheet if you want, near where I have a home in Seward, Alaska. And a couple of falls ago, I actually got to participate in a research project that took me out onto the Harding ice field, where only the summits of ice-buried peaks, otherwise known as nunataks, breached the ice. And it was easy to imagine I was in the Ice Age Catskills. So, 20,000 years ago, if you were standing above Phoenicia, you might be standing on a large ice sheet like you see in this image. So during the Pleistocene, continental ice sheets and glaciers advanced and retreated many times, embellishing the stream-dissected mountains and valleys, leaving a legacy of sediment and landforms that today's streams are still processing. So here's an example. This is the Westkill in the Schoharie Basin, and we're seeing some erosion into some glacial legacy sediment in that high terrace there. Those deposits were largely deposited during the Pleistocene, although the deposits up on top, which are stream deposits, you can barely see that up there, those would have been formed after the ice left. But another example is the muddy water. Most of the silt and clay that's creating that turbidity is actually coming out of eroding glacial lake deposits upstream. And that's what we're going to cover with this chapter. So we know the Catskills and New York have been impacted by multiple periods of glacial advance and retreat over the span of 2.6 million years. While the geologic record of glaciations prior to the last big advance is not well preserved in the Catskills, we do know that around 25,000 years ago, the ice sheet reached its maximum extent into northern New Jersey and Long Island. That would be that image on the upper left. These simplified maps are adapted from the New York State Museum's publication titled Geology of New York, a simplified account. They show the potential ice margins and time periods that at that time the scientists had put together. These interpretations are actually now dated, and Dr. Andy Kozlowski of the New York State Geological Survey and Museum is working with others to revise the chronology of ice margin positions. But for now, this series of maps are actually still useful for showing that by at least 15,000 years ago, the Catskills were free of glacial ice, and streams resumed the geomorphic work of shaping the landscape. The geomorphic work included erosion into glacial legacy sediment, the sediment the glaciers left behind. And we're going to focus on two categories of glacial legacy sediment that we typically encounter along streams: glacial lodgement till and glacial lake sediment. So the glacial tills of the Catskills. If you see an eroding and typically high stream bank that has an almost concrete-like composition, almost rock-like composition, but isn't rock, you're most likely looking at lodgement glacial till. So the glacial legacy includes these thick deposits called glacial till. And in this particular case, we're going to focus on lodgement till. And it's composed of unsorted sediment that ranges in grain size from clay to boulders. It's not stratified, it's not layered, there's not boulders and then clay. You typically have a matrix of very fine sediment with coarser sediment embedded in it. You can see that really well in the middle photo and the photo on the right. And much of the sediment we actually see in today's streams originated from this glacial source. So there's a lot of this lodgement till in the valley bottoms. And you might recall several slides ago that I showed a superficial geology map in the Schoharie, and it showed how much glacial till is in the valley bottom. So that's where a lot of sediment that the streams are still processing originated. The way that this works is that you have thousands of feet of glacial ice moving across the landscape at its base, entraining sediment, grinding it up, mixing it up, creating this incredibly dense slurry. And under all that pressure, you get this super consolidated deposit. There are a lot of other kinds of tills formed in New York and in the Catskills, but we don't often see those in the stream channel. So if you're out in the stream and you see a glacial till, it's most likely this lodgement till formed at the base of the ice. So streams have been working their way through the dense lodgement glacial till for thousands of years and still have thousands of years to go in processing the glacial sediment. All right, so the map, this is going to be about the glacial lakes of the Catskills, which is what I primarily study. And the glacial legacy of the ice ages also includes these variably thick deposits of lake sediment. What does lake sediment have to do with glaciers? Well, as I've wrote here, it's from these valley-filling proglacial lakes and smaller isolated lakes that meltwater from the glacier gets trapped in these valleys because the ice margin has blocked it off. So the image on the left is just a cartoon image. It's not representing reality here, but it just shows how glacial meltwater can actually get trapped in these valleys and create these large lakes. The image on the right shows that you can also just have smaller impoundments. So this is another image from where I live in Alaska. This is Godwin Glacier, and you can see how completely full of silt and clay these lakes can be in that image. So that grayish color is just thick with silt and clay. And those settle out to form the layers of silt and clay that we see today. And the most common evidence for glacial lake sediment occurrence is through erosional exposures in streams. So these are 3 photos that show examples of glacial lake sediment exposed in eroding stream banks. Whether they're large or small lakes, they're filled with muddy glacial meltwater. And the glacial meltwater streams, when they're active during the melt season, would be loaded with sand and silt and clay. It would be continually highly turbid, meaning very muddy, very difficult to see through. And they would deposit the silt and sand in these warm seasons, and maybe some clay would settle out during that time. But during the non-melt winter season, the clays that are still in suspension in those lakes would settle out and they'd form clay layers on top of the clay, sandy, silty layers. And a pair of these 2 layers, the clay layers and then the sandy, silty layers, they would represent an annual cycle. So we can actually look at the duration of some of these lakes by looking at the numbers of those layers. And those coupled layers we call barves or rhythmites. So they tell the seasonal story. You can see an example of that on the left of that melt season and that frozen season. And in this image, which is a photo I took from the Beaver Kill, there's also a drop stone, which is just above and to the left of that pen that's there for scale. That melted out of an iceberg and dropped onto the lake bed. And you can even see how it deformed that lake bed sediment. The image in the middle shows a highly deformed deposit of glacial lake sediment that's exposed in the Batavia Kill at the base of the Red Falls Glacial Moraine. There's evidence that this lake was actually overridden by an advancing lobe of ice that subsequently deformed the layer. So this is a good example of where a lake formed in front of an ice sheet that was advancing and actually got overridden. And eventually, as the lake retreated, you ended up with this very deformed lake sediment. The photo on the right shows an example of glacial lake sediment exposed in an eroding bank that is part of what we would call a rotational mass failure. And these erosional sites actually tend to be the chronic, long-lasting sources of elevated stream turbidity, which is at the heart of the research that I've been doing for the last 10 years. So that's our background on the geology. and geomorphology of the Catskill Mountains. So let's step into some streams to see what we can see. We're going to come back to this photo in a subsequent slide, but for now you might note that the apparent gravel bar I'm standing on includes a lot of rocks that are not sandstones or mudstones. We're going to start with what we can learn from investigating a cobble or gravel bar. And what is a cobble or gravel bar? Stream bars, depositional bars, are typically elongated depositional features where stream transported sediment is temporarily stored between flood events. They can occur along channel margins as point bars in meander bends, or lateral bars along straight reaches, or as mid-channel bars that often form as stream flow separates around an in-stream obstacle or an abrupt increase in channel width. So I have an example of a mid-channel bar in this photo. You can see flow going around both sides of it. Gravel and cobbles are defined by their size range. And I have some examples here later if we need to, but gravel is greater than 2 millimeters. So below gravel is sand, which is less than 2 millimeters, but gravel is also less than 64 millimeters. So gravel fits easily in your hand, while cobble is the next size class up. You can hold the smaller cobbles, which are from 64 millimeters up to about 256 millimeters. That's bigger than your hand, and you might need two hands to hold that. So that's what we're talking about. There are many stories to find in a single stream cobble bar. Streams are the conveyor belts of the sampled terrain. So if you visit any Catskill stream sediment bar and almost every rock is either sandstone, conglomerate, or mud rock, we are seeing the rocks that make up the Catskill Mountains. And this is just two photos that were taken near each other. There's a cobble bar with sandstone, mud rock, and at least one conglomerate near my shoe for scale. And then there's an outcrop not far from here of sandstone, mud rock, and sandstone. Here are 4 photos of cobble bars on 4 different Catskill Mountain streams. And if we took a statistical sample of these rocks, we'd find likely that 90 to 99% of the rocks are sandstone, mud rocks, or conglomerates. However, there are some differences in each of these cobble bars. I'm going to focus on one of those differences. The rocks on the Plattekill, Woodland Creek, and Westkill cobble bars, and those are labeled, have been transported in a stream for a very long time. They're rounded. Their roundedness tells us this, and as they make their way downstream, while the Stony Clove Creek cobble bar, the second photo, has very angular rocks, indicating they actually have not spent much time in a stream at all. So how did they get there? Well, just upstream of this bar is a large landslide in glacial till, and these rocks originate from there. So we can use cobble bars to make some inferences on the geologic history. So in the case of Stony Clove, not only do we get the story of the Devonian River environment recorded by the rock types, but we actually also get an Ice Age story recorded by the rock shapes. So when I'm out there and I see something like that, I'm going to go look for that source. I'm going to find that exposed glacial till that contributed these rocks to the stream channel. Now, of course, not all rocks in the cobble bars originated from the upstream bedrock in the Catskills because the Ice Age glaciers that originated north of the Catskills delivered rocks from outside the area. The 2 photos on the left show examples of these glacially sourced visitors. We can call those exotics if you want. The circled rock in the first photo is a metamorphic gneiss from the Adirondack region, and the circled rock in the second photo appears to be from the Potsdam Sandstone Formation, also from northern New York. The other circled rock in that second photo is of concrete, a human sourced rock. And if we're fortunate, we can also find a dramatic story like the third photo that has the boulder that I'm standing on in that photo just a couple of slides back. That's part conglomerate on one side and part sandstone on the other. This is kind of a record, most likely, of a Devonian flood, where there's an abrupt change in stream bed as a massive amount of coarse sediment was brought in. I didn't get to see the outcrop that this originated from, so I don't know that for sure, but that's my interpretation. The last photo shows a common exotic rock we find in Catskill Mountain stream cobble bars. I'm sorry I don't have a great photo of it, but you often see bank protection in the Catskills along roads, along people's property, formed of riprap rocks that have been quarried outside the Catskills, and limestone is a very common rock used for riprap and bank armoring in the Catskills. So we often find a lot of limestone in these cobble bars, and often that's happening downstream from some bank protection source. All right, here's an example of one of my favorite Catskill rock types. It's a form of conglomerate. but could also be considered a breccia. It's formed of mostly angular, broken rock fragments held together by a sandy cement that works as a rough definition for breccia. In this case, we could actually call this a mud-clast rip-up breccia, recording the deposits following a flood powerful enough to scour and erode a dried out fine sediment floodplain. So all of those fragments in there originated from outside the channel, were brought into the channel, deposited, buried, and subsequently exhumed hundreds of millions of years later. And I might be right about that. I might be wrong. That's part of the fun of the geology and getting more and more experience in streams to help you understand the possibilities of what we might encounter. Here's an example of a large mudstone rock that has a kind of stippled pattern. You can see those little white dots. The stippling is actually the weathered expression of fossil root casts from a Devonian riparian forest. This is actually one of the most common exotic rocks brought into the Catskills by the Pleistocene ice sheets. Garnetiferous gneiss. It's a metamorphic rock from the central Adirondacks brought by ice, buried until, and then released by post-glacial fluvial erosion into Esopus Creek in this instance. All right, so moving on from cobble bars, let's look at some other features we can see in streams. These are photos of plant fragments that were entrained into those ancient Devonian rivers and deposited as part of the material those streams conveyed. If you step into any Catskill stream today, you're likely to see this same thing happening. All right. And wood in streams is an integral part of the aquatic ecosystem. So when we see these fossils, we're looking at components of a Devonian aquatic ecosystem. These are photos of fluvial forms, stream forms, bed forms, observed in the Devonian River sandstones that show fossil ripples on the left in the Platicille and migrating sand dunes in plan form and cross-section on Biscuit Brook in the middle, and a photo of a fossil muddy floodplain with desiccation cracks from when it dried out. And I can't really quite tell from here, but you might be able to see the traces of roots from that Devonian forest in that image. I'm going to close with just a few more slides. I'm going to focus on one of the most beautiful aspects of the Catskills, and they're flush with waterfalls. You can often see that the upper portion of the waterfall is layered sandstone or conglomerate, and that the lower portion may be some variation of a mudstone or a fine-grained and more easily weathered sandstone. Waterfalls are fabulous places to learn more about the geology of the watersheds in the Catskills. Here's some photos of some of the many waterfalls you can find when hiking in the Catskills. Next time you see a waterfall, take the time to check out the bedrock geology. Can you find the story that might explain the fall's presence? And remember that though waterfalls might seem like unchanging features in the streamscape, they're actually nick points in the upstream migration of a lowering valley bottom. And if you get a chance to hike in the Platte Clove, a streamscape dominated by waterfall after waterfall, you can see evidence for this upstream migration of the waterfall. Another wonderful fluvial feature in Catskill streams are the many bedrock flume channels. Flume channels are channels incised into bedrock, typically following fractures or zones of weaker, more erosion-prone bedrock. Biscuit Brook in the Neversink watershed has some of the most amazing flume reaches I have encountered in the Catskills. And in this case, the two photos on the left are actually within the Stony Clove watershed. The photo on the bottom is one you can just access right off of New York State Route 214. The photo on the upper left is in Warner Creek. That's a tributary to Stony Clove Creek, and it's on state land and is accessible. The two other photos are in Biscuit Brook. One shows an example of a stream occupying a vertical fracture in the bedrock, and the other shows a flume channel being formed in the more easily erodible mudstones. Okay, we're going to 2 slides on glacial legacy sediment and we're done. Streams offer us some of our best opportunities to investigate glacial geology. The photo on the left is of glacial lake sediment that has clearly had an active history after the initial deposition into flat horizontal layers. What could have so dramatically deformed these lake sediment layers exposed in the toe of a stream bank on the East Gill? The answer is reached in this location by noting that it is beneath the massive deposit of lodgement till shown in the central photo where I'm standing in a very dangerous location. The lake was the result of glacial meltwater being impounded between the mountain valley slopes and the glacial ice margin. The glacial ice advanced, overrode the lake deposits, very similar to that Batavia Kill example. And the incredible shear stress at the base of that mobile layer of sediment that's incorporated into the base of the ice, that's our lodgement till, was capable of folding and faulting the lake sediment into these wild sculptural exposures that are only present for a brief time between floods. We get this transient geologic art. The photo of the turbidity plume on the right is an example of how very fine sediment stored in glacial lake sediment for thousands of years can be released into today's stream. It's like a temporal link to the past. In fact, we can go back even further with our temporal connectivity. The lake sediment that sourced this turbidity plume had a prior history of being ground into glacial flour, silt and clay, after it was eroded by glaciers from Catskill bedrock. And that bedrock was most likely a mudstone where it had been stored for hundreds of millions of years. And before that, it was eroded out of those ancient Acadian mountains. And of course, we can keep going. These silt and clay particles have had quite a history, and now they're on their way to the next long-term storage site. And I added this last slide because this is what I did today. These photos are from today's fieldwork. This is a set of photos from the Beaver Kill with the very excellent 2025 Watershed Conservation Corps, a group of SUNY Ulster College interns that help us with our summer field research. Declan there on the upper left is performing a very competent tree pose on top of a boulder in the Beaver Kill in Mount Trimper. A close examination of the boulder finds that it's a Devonian sandstone with fossil wood fragments in the Devonian stream sediments. You can see me pointing to that in the middle photo there. And glacial striations from its history as a boulder in the mass wasting glacial deposit. So on the right, I'm showing scratches that were gouged into this rock as it was carried by ice. And then its source is that high bluff you can see on the bottom photo there. It came out of that mass wasting. So you kind of get a full story here of the history of this rock. All right. So where and how to explore Catskill streams? Well, many Catskill mountain hiking trails often follow alongside streams. Those are the blue lines on the map. Some great examples are listed here, but most Catskill mountain trails give you access to streams. There's lots of waterfalls to visit. I've listed a few here. What do I like to bring out with me? Well, I like to have maps. I think I've made that pretty clear. And if you're tech savvy, there's actually free software out there. QGIS is an open source GIS software, and you can access data layers from the New York State GIS Clearinghouse. So there's videos out there on YouTube that tell you how to make your own maps, and you don't have to spend money on the software to get it. Come prepared to get wet, and definitely be prepared for slippery streams. So use something grippy and clothes that are quick for drying. I also like to bring tools with me if I'm specifically going out to examine a stream to learn about the geology. I'll want to bring something to break open some rocks if I need to understand a little bit more about the rock type. I like to have a magnifying glass to help me identify fossil plant fragments. I always have my camera and field book. And I also bring something for maybe clearing off an exposure in a stream bank that's not so clear. I'm going to close on this interesting and unusual orangish sandstone in Biscuit Brook. And here's a list of some recommended reads and online resources. Catskill Glacial Geology by John Rich in 1935. Believe me, it is still the best source on the history of the Catskills in the glacial period. Beneath It All, Bedrock Geology of the Catskill Mountains and Implications of Its Weathering by Chuck for Straeten is a great resource, and that is available. Just Google it and you can access it if you really want to get into the deeper dive of the bedrock geology. If you want to learn more about the Panther Mountain circular feature, there's an article by Ingvar Isaacson and others in Northeastern Geology. Again, Google that and you'll be able to find it. Any of the books by Robert and Joanna Titus offer an entertaining and informative account of Catskill geology. And then if your interest is more academic, I recommend the book by Steve Shimrich, Billion Years of History, Geology of the Hudson Valley. Steve is a geology professor at SUNY Ulster, and he has a chapter on the Catskills in that area. There's a lot of online resources. I really recommend checking out the New York State Museum and Geological Survey's website. It's great information, resources you can download or purchase. Also, check out catskillstreams.org. It's a hub that can connect you with all the stream management program websites hosted by Greene, Ulster, Sullivan, and Delaware counties. And several of the programs actually have very productive YouTube channels with great videos on streams and geology. So I want to thank you. And I also want to thank my friends Chuck and Andy of the New York State Geological Survey, my Catskill Stream Management Program colleagues, and the many college students I've had the privilege to study streams with over the past 25 years. But I also want to thank Woodland Creek and Warner Creek. Those are the two streams I have learned the most from over the past couple of decades. And I offer my contact information here if you have any questions or want to go visit a stream sometime. Thank you. And sorry it took me 5 minutes longer than I planned.
Yay. Thank you, Dany.
Oh, you're welcome. Sorry, that took a
That
little
was
bit longer.
no
I
worries.
probably
That
should
was
have
excellent.
practiced a little longer.
No, that was so great. Thank you. Thank you
Okay.
so much. So looking at the Q&A box, I do see one question here. I
Okay.
also just want to add that any of the links or resources that you provided, I will be sending a follow-up email tomorrow. So I'll throw those out there again for folks
Thank you.
in case
Yeah.
they missed. Yeah.
Yeah, I tried to get
Um,
to that this afternoon, but I didn't get there.
no, no problem. Okay, this question came in. Today, people find Devonian saltwater fish fossils in the Catskills at 1,400 feet above sea level. Given these fish lived at sea level 380 million years ago, what forces have caused these fossils to be uplifted over millions of years?
Could you repeat that question for me? Because
Yes,
I'm probably not going to be able to answer that question.
that's
But
fine. Today, people find Devonian saltwater fish fossils in the Catskills at 1,400 feet above sea level. Given these fish lived at sea level 380 million years ago, what forces have caused these fossils to be uplifted over millions of years?
okay, so I think I can address part of that, the uplift part. The saltwater fish part, that's news to me about, especially at 1,400 feet elevation. That would put you probably in the Walton Formation, which is definitely terrestrial river deposits and not saltwater deposits. So I'd love to learn more. So you have my contact information. Please send me more information. But the uplift, that's a great question. It's one that I would really prefer to defer to Chuck. But there, as rock is eroded away from the Earth's surface, we are unloading the Earth's surface, right? We are creating an opportunity for the Earth's crust to rise up slowly. And so you get this isostatic uplift that brings the rock up. And as you remove more and more sediment, you can actually increase more and more uplift. That's part of how those joints can form, those vertical fractures that we were talking about. The most recent uplift probably, which wasn't substantial, but was definitely worth noting, was once all of that massive ice was removed from the landscape, you get this glacial rebound, this isostatic rebound from the removal of the glacial ice. But the tectonic story of that still remains a mystery to me. You know, I focus mostly on streams. I'm looking at the landscape being formed today, and I know enough about the bedrock geology and the uplift history to give me a sense of it, but not really to be able to answer your question satisfactorily. So sorry for that.
Um, I think that's okay. Chuck is on.
Oh, great.
Maybe if I can invite him to speak if he's interested. But
Sure. And I can
while
even say to Chuck, Chuck, can you tell me all the things I got wrong? That would be really helpful.
no, great. Okay, so I'm gonna do that, and I will also for Chuck, if you can hear me, I am inviting you to speak. Okay, so it says that Chuck will be rejoining as panelist, so we'll see how that goes. For now,
Okay. All
what
right.
is your
Okay.
favorite geologic feature to find while walking streams?
What is my favorite geologic feature to find while walking streams?
Oh, so
Do I have
good.
to pick just one? All right, if I had to pick just one favorite geologic feature, well, for me, it's bedrock streams. While glaciers are what brought me into geology when I lived in Alaska. That was what kind of pulled me in. But bedrock streams, particularly flume streams, flume bedrock channels, just resonate with me. There's no geologic reason for why I'm all excited about them. It's just those are my happy spots. Okay. Hey Chuck,
Cool.
good to see you, man.
Hey, Danny. Hey, Em.
Good. Hi.
I
Well,
Hi.
did
Hi.
I didn't mention this, but Chuck and I have been friends since 1988 and have explored lots of geology together through the years.
Yeah, yeah,
I look at the stuff on top of the bedrock, and Chuck looks at the bedrock. So together we can pull together a story.
that's
yeah.
the year I was born, so
Oh,
Oh,
thank you,
yeah.
all
all
kids.
right,
Such a
all right,
kid. Such
all
a
right.
kid.
We're a
Yeah,
bunch of
Love
Devonian
it.
fossils, the two of us.
yeah, 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 yeah.
Awesome.
So can you answer that
So
question?
yeah, with the fish question, the fish topic, how did the person know if they were freshwater, saltwater, or in between the two, brackish, fish that lived in brackish, fresh, or saltwater environments? So that would be the question. Now, you think about the Hudson River, it's a lot different because it's not coming out of a really big mountain belt. But the salt water, or at least brackish waters, mix of fresh and salt, comes up the river a good ways. But this is a very different river than coming down out of the mountains. That in New England might have been on the order of the Andes Mountains. So very different situation. So you have to know which kinds of fish you're looking at, and I can't even begin to talk about that.
Yeah. Are
That's
you
not my
aware of
experience.
any saltwater fish found in the Catskill Mountain
No,
formations?
I don't, but I don't know that much. There's down
Yeah.
in Pennsylvania, there is a person who was a modern fish specialist at one of the colleges down there, and he's turned into a Devonian fish expert.
Oh, fantastic.
Hopefully this summer we'll get him and a bunch of other people who work on the Devonian terrestrial rocks deposited on land with the oldest forest and stuff still.
Yeah, I know you and I found some uh fish scale, I believe fish scale fragments. Was it in the Plattekill or it was something below the Ashokan spillway area when we were doing some
Yeah,
field work together. So
yeah,
that's
right.
further down in the sequence, not in the High Peaks area.
Yeah, yeah,
But yeah.
yeah, yeah. Um, no, even on Thursday last week, I found some fish fossils that would be from the marine and terrestrial transition zone, where you could have maybe saltwater or freshwater or the mixture of the two to make brackish water.
Okay.
But that was the marine rocks with the shelly fossils and everything were a little below that.
Got it. Okay.
The other thing I might bring that I would like to bring up is the Panther Mountain structure. It does have that anomaly as far as jointing, but if there really was an impact event, it would completely disrupt sediments and even sedimentary rocks, and it would spread for 100 miles deformation, perhaps,
Oh,
depending on the site.
absolutely.
Yeah, so
Yeah.
I when I came back to the State Museum in 2000, that was one of the things I really wanted to look into, and I just never found any evidence in the sedimentary rocks. I mean, you smack hit the earth, and you're going to just, especially loose sediments, you're just going to send tremendous amount of stuff
Oh
into
yeah.
the air to be scattered for long distances. There's nothing like that in New York's rocks. Devonian or Silurian period older than that, or Ordovician. So
Yeah, you and I have talked about this for years. We both have
yeah,
been
yeah,
fairly skeptical of it, but
yeah,
I brought it in because it's one of the most common questions I get. And,
yeah,
there were other lines of evidence that they used. They used the gravity anomaly below Panther Mountain. They used the limited access to drill cuttings that they had to look for some shocked quartz, but
yeah.
there really wasn't any evidence. And I have walked every meter of Esopus Creek and Woodland
Mhm.
Creek, to where
Mhm.
Woodland Creek originates just below Slide Mountain summit. And I have not seen that increased fracture density. So I don't know that this is the example or explanation, but I just love the idea that geology is also an imaginative science and allows us to think about origin stories. So for me, it's a little bit of an origin story. It's a bit of a myth, but
Mhm.
I don't know what the truth is. I don't know what caused that unusual feature.
Yeah. The anomaly that was projected is actually where the Black Marcellus Shale, which was mud originally, comes to the top of the Onondaga limestone.
Yes. Yep.
And that should have been very clear. I've looked at the record of the hole that was drilled on Panther Mountain down deep, and there's no disruption in the sediments. The sediment layers are just like they would be in the Schoharie Valley. Yeah, so
Yeah.
that
Thank
one
you.
that one just doesn't seem plausible at all.
Yeah, it was interesting. I thought about keeping that slide in or out, but with an hour to cover
Yeah,
so much terrain, it was
yeah.
I kind of had to bring it to the sort of the point that I wanted to raise is that um, the the fracture network in the Catskills is a significant influence on the valley and mountain formation
Yeah.
orientations that we see. So there
Mhm.
is an origin story for that annular drainage.
Mhm.
I may not find out what it is
Yeah,
during this lifetime, but I hope that, someone uh, kind of adds to the canon, if you will.
yeah.
Yeah.
I talk about this in a section of the big 2023 um, paper that I put out within the big Devonian of New York volumes, 3 volumes, over 1,000 pages. I laid out how I see it, and it
Oh,
just
okay.
doesn't seem plausible.
It's so funny. I have not seen that yet, so I have to
Yeah,
take
I
a
was
look at
just
that.
thinking the other day if I sent that to you or not.
No, sir, you have not.
Such a poor friend
I
in
want to
fear.
see it too. So that person with the fish question followed up. I guess my question is, what uplift forces has caused these saltwater fossils to go from sea level to hundreds of feet above sea level? Have the Catskill Mountains ever undergone a mountain building event that caused this uplift?
No, not like you would get in a mountain belt, like what happened in New England in the Devonian and all the way from East Greenland to Alabama. There were smaller continents colliding with Eastern North America at that time. And that formed mountains that would be all disrupted as far as layers and stuff, and the rocks that were there that were even sedimentary rocks, shale, limestone, etc. They were metamorphically altered by being buried under, I forget the rocks that are at the surface of the Appalachians right now, like in Massachusetts. It was miles and miles and miles. Those rocks were miles and miles and miles below the surface at that time. As Dany has told us, basically the mountains, and he did a great paper looking at both sides of this. What are the Catskills really mountains technically? Well, it's a dissected plateau. Picture a paperback book, okay, and it's all level at the top. And then you take an X-Acto knife and start
No.
cutting these down through it. Do an old stupid book.
Yeah. Actually, this
But
is the dictionary of geological terms, but yes.
yeah, but you could cut
Um,
down through that and make valleys, but leave peaks and ridges.
Right. And so that paper that I wrote was, what is a mountain, right? How do you
Yeah.
define a mountain? Is it a topographic definition? Is it a process-based definition? If we just look at the forms, the Catskills are mountains.
Yeah.
They are topographically mountains. Did they form through the typical compressional tectonic processes that we see in a lot of the big mountain orogenic belts? No.
Mhm.
Um, were they like the extension kind of situations you have where the Earth's crust is spreading and you get, the basin and range kind of mountains that we see, or were they volcanic? No. So they are a unique kind of mountain range. I think the Ozarks are somewhat similar in places. There's examples around the globe of these dissected plateaus that sculpt mountains out of it. So it's not so much about, as Chuck was saying, those compressional tectonics, but there was an uplift process that did bring the Earth's surface up,
Yes.
right? And
Yes.
so, and what I was just trying to do was the simple math of you've got two forces, the forces that bring it up and the forces that work to bring it down. And in the Catskills, you had this sort of maybe slower uplift process, but the rate of the erosional process exceeded that, and it created and sculpted out these mountains. And it
Yeah.
took tens of millions of years. And glaciers definitely had a dramatic influence on the mountains we see today. But actually, we're doing some geophysical, USGS is doing some geophysical work. And they're finding that some of the valleys, like in Woodland Valley, I believe, the depth to the bedrock there, the original valley bottom before the Ice Age deposits is over 200 feet, right? So we actually probably had mountains that had even greater relief prior to the last ice age. What we don't know is, through that 2.6 million years, how many times ice came in and out of this system, right? So
Yeah.
we really, in the Catskills, as far as I understand it, really only have a solid record of the latest advance, that Wisconsin and, Laurentide ice sheet advance.
Yeah.
Yeah. And
About the uplift of the Catskills, when you load a big mountain belt on the crust, that's a great massive weight that causes the area around it to subside and be kind of like a moat to the sides of
mhm.
the mountain ridges. So the rocks, basically the seaway, well, I don't want to get too complex, but as the mountain belt would erode away, then there would be less weight on the crust. And this even happened with the glaciers, the last glaciation. When you had a mile of rock over the top of Albany, let's say, or Catskill, that massive weight of ice caused the land to subside. And so, for instance, Lake Champlain was salt water for a time until the ice had melted far enough north, and very slowly the lake rose up again, and you didn't find whale fossils and seal fossils and fresh and saltwater clams and things like that in the lake anymore. It was fresh water again.
Yeah.
So part of unloading the crust permitted the Catskills to rise. And I think you maybe mentioned this, Dany. You did. That it's estimated by two different methods that there was 2.5 to 3 miles of rock on top of Slide Mountain that's eroded away over the last, say, 300 million years.
Yeah.
And one person is playing around with the idea that perhaps it was much more than that rock on top of Slide.
Well, there's a tremendous amount of missing geologic record between the Pleistocene and the Devonian.
Yeah,
So,
yeah.
so we don't really quite know what was here, but certainly there was something here.
If you think of the Cairo fossil forest that uh, Amanda has organized for me to lead people into on Saturday, it filled up very quickly. But I'm planning on doing one or two more this year, one in the summer, one in the fall. But anyway, that level is on the order of 385 million years ago. The first dinosaur fossils are only 230 million years ago. So this is long before the dinosaurs. And we could talk for hours.
Yeah. I'm also going to mention, we had planned for me to do a stream geology field day
Yes.
this spring, but we postponed it, fortunately, given the kind of wet spring we're having. But I am still going to offer to do that. So if anyone's interested in getting out and doing a stream walk and talk, and we're going to try to pick a stream that's going to give us examples of some of the glacial geology you can encounter, some of the bedrock geology. And really what I focus on isn't that bedrock or that glacial, but I like to study the actual stream geology. I like to understand how streams are made, how they're processing that sediment, how their forms come into being, what's the trajectory of a stream. So my work is all about reading the modern landscape. And then the role of the geologic history in influencing that landscape. So really, I'm looking at really today's geology. So that's what a geomorphologist often does.
That will be a very good walk.
Yeah, we have to after we get past oh yeah, how do we stay informed about the future stream walk? So once we get past this weekend and things settle out a little bit, we are going to try to get out in the field and identify a stream that would be best for that event. And then I will be sharing that information through the Greene County Soil and Water email list and on our social media and such. It'll be on our website. So keep an eye out for that later in the summer, I think is probably best.
Yeah. My field season just kicked off, so
yeah,
I'm going to probably need a couple of months just to get through that.
totally.
All right.
Yeah, we
Dany?
haven't.
Dany, a tremendous job here. Great graphics, great discussion of things. Yeah, excellent.
Yes.
Excellent.
Well,
Excellent job.
thank-
And yes, that's come through quite a bit in the chat here. Thank you so much. Very informative, great presentation. Laura Davis says Chuck and Dany could have a great podcast. I agree. This is the first time I've really felt like I've been in a podcast. It was really fun. This little moment.
Well, there you go, Amanda.
Yeah.
Future project for you.
There we go. Yeah.
Amanda,
okay, so, yes.
thank you very much for organizing both these talks and the visits out into the field at the streams and this Saturday at the Cairo Quarry and up the hill from there.
Thank you.
Yeah,
My
we really
pleasure.
value the work you're doing, because it's, we would do our work anyway, but it's fun to be able to share it.
Yeah.
Well, I appreciate you both sharing it and being here, and the opportunity to learn from you both is always, incredible. So thank you, as always.
All
See you all
right.
soon.
All right.
Thanks for everyone for joining.
Bye, everyone. Thanks for coming, joining.
Take care.